Hello again, everybody. Today in this video I'd like to just focus on the math of the globe Earth and kind of show how I'm coming up with what I think should be the curve of the Earth. There's been a lot of comments that are saying that, oh, you're using the wrong curve, you're using the wrong formulas, you need to do this or that. So I just want to show how I'm coming up with my calculations, and we'll go from there. So the first thing you do is look up the Earth's radius. Well, what's the Earth's radius? Well, it comes up with 3,959 miles, 3,959. That's an average, because it is, what they're saying now, is a oblate spheroid. It's shorter at the poles than it is at the equator, and so it's a little bit different. So the mean radius is 3,959. It's a diameter difference of 26 miles, meaning it's only 7,900 miles at the poles, but 7,926 miles at the equator, which makes a difference of 40 miles in circumference, because you have the circumference of the equator at 24,902, and pole to pole is 24,860. Okay, whatever, that's fine. I'll show in my calculations later that it doesn't really matter for relatively short distances, and I mean relatively short distances is 500 miles. You go to 2,000 miles. Okay, there's a little bit of difference, but still it's insignificant. But I'll go over that in a little bit. So this is just showing that, okay, 3,959, and that's what I'm using right here is the mean radius of the Earth, 3,959. So that's what I'm using in all my calculations. So we've got the Earth radius to deal with. Then to figure out the circumference of a circle, you take 2 pi times the radius. So 2 pi r, and then come over here and say, okay, so 2 pi r, 3,959 is 24,875. So that's really the circumference that I'm going to be using in my calculations in my picture that I show, my CAD drawing that I've done. This is what it would be at the equator, meaning 3,963, 24,900. Okay, so it's a little bit different, 25 miles, not that big of a deal, okay? But I'll go over that again in a little bit. So let's first go to figuring out the height, how people are figuring out this drop, or what you want to call a drop, height, whatever you want us to call it. I don't know how to say this word. I call it Sagita. That's how I say it in my mind. So to figure that out, you have this formula here, which is the radius minus the square root of the radius squared minus the half chord length. If you come down here, it's right here. Radius, square root of the radius squared minus the half chord length. Okay, 1/2 distance across the entire base of the arc. So we're looking at this whole thing. So what you do is you take that radius, and what I've done here, I'll just do this here, what I've done is I've made this formula in Excel to show what this Sagita, what this drop really is, because a lot of people are saying it's 8 inches times the distance squared and blah blah blah. It's close, it's not correct. Okay, this is the correct formula that you've got to use. So what I've done is I've plugged this formula in here to say, okay, the radius, which is 3,959, sorry, I was playing with that earlier just to show the difference, 3,959, okay, and I've just made this into feet so we can kind of see the calculations later on, and this will make a little more sense. So 3,959 times 5,280, because that's how many feet are in a mile, gives me 20,903,520 feet as the radius. So now if I take that, so in my formula I take the radius minus the square root of the radius squared, so minus C14 squared, or C14 times C14 minus, and then C17, which is the feet, and times C17, which is the feet, or in this case, the half chord length is miles. So what I've done is I've taken this feet so I can see how many miles, so if I want to look over 5 miles, 10 miles, 12 miles, 15 miles, whatever that is, so we can come up and we're in the same denomination here though. So 3 miles is 15,840, obviously 1 mile, 5,280, just so we can see this good. So if you plug this into the formula for this zeta, you come up with, at 1 mile, you come up with 0.67. Well, what's 0.67? Well, this is in feet, so then I come over one more cell and I said, okay, well, I'll take that calculation and times that by 12 to come up with inches. So that's 8 inches. And I think everybody agrees the first mile is 8 inches. And I think everybody's agreeing on what this curve should be. So the first mile is 8 inches, second mile is 32, third 72. So you can see that we just go through here. After 5 miles, it's 200 inches. Okay, now inches, I don't like playing with inches anymore. I'll jump back to feet. It's just a little bit easier to deal with feet and knowing how far that is. So after 5 miles, it's 16.67 inches. Now you say, okay, is my formula really correct? Well, the nice thing about that is you have this thing down here. We can delete this. So the radius, I was messing with this. The radius is, what do we say, 20,903,520 inches. Not inches, sorry, feet. And my half chord length is whatever we want it to be. So if I want it to be 1 mile, we're going to say 5,280. And we hit calculate. Well, that's 0.6668. Well, that's exactly what I came up with this. I've only gone 2 decimal points. If you go in further, then it does actually go to 0.6668. I've just limited it to 2 decimal points to show that. Okay, so let's check this at, let's see, 5 miles. Make sure we're still, so we should come up with 16.67 feet, right? So at 5 miles, we got to plug in here 26,400. Calculate 16.67. Okay, so my calculations are doing all right here. Let's just test one. Let's take 80 feet. So just to make sure my calculation, my formulas are working correct. So we're going to say 422,400. Calculate. That's 4268. 4268. 0.18. So my calculation is correct. My Excel formula is doing the same thing that this formula is doing. So I know that I'm using the same formula and I'm calculating what the curve or what the sagitta, what the height should be, what the drop should be over a distance. So I say my drop from this point over to this point, if my radius is 12 and this is 9.6, this is miles, this would be miles, 4.7. So what I'm basically calculating is this line right here. And this line, if I draw a straight horizontal line across here and drop down, should be exactly the same. Okay, so 4.7, it should just be a square. Okay, so what I'm saying is you stand right here, pretend wherever you're at in the earth is the top of the earth. You stand here and look out. Well, over a certain distance, the earth is going to fall away from you. Okay, so what I have done to test that, I've done the calculation. You can see I've done every single mile here, every single mile, and this one goes all the way down to 500, and I've done that in 500 increments to show what this sagitta or height of the earth should be. So I've done that for every single mile, all the way up to 3,959 miles. And if we come down here, 3,959, the sagitta is 3,959. So there's the sagitta in miles. That equals each other. So this means if I look out, the radius is 3959. Go out 3959, it'll drop 3959 and hit the exact point. 12, 12, 12. So that's what I'm saying I'm matching. It's 39, 59, 39, 59, 39, 59. Okay? It's all the same. And to how I've verified that once again, not only by the calculations, is I've done an AutoCAD drawing. And in this AutoCAD drawing, I have drawn this Earth to scale. So if I click on this Earth that I've got here, it is, my radius is 20,903,520, which matches what we were saying here, back over on this thing, at 20,903,520, okay? So this Earth is to scale drawing. What I've done is I've taken certain lengths and I've measured out the distance just to see, okay, let's see if this really works out. So we come in here and I say, okay, 5,280. If I remember, a drop for that is 8 inches, right? 1 mile, 8 inches. Okay, and I've already dimensioned these out just so save some time. You don't have to do it. Click on that, 5,280. Okay. So I've drawn this out, and I come down here and say, okay, well, how far of a drop that is that? Well, it's 8 inches. So here's my distance going over. Here's my distance going down, which is 8 inches. This white line is the Earth. If we zoom out, you can see that it's selecting the whole Earth. Okay? So that's what the light line is. This yellow line is the line horizontal, straight 1 mile. And this other yellow line right here, sorry, I picked the wrong yellow line the first time. That one. Okay. And the drop is that one. Okay, so now that's 1 mile. We check 2 miles, 10,560. Okay, we should get 2 foot 8 inches. Let's check that. 2 miles, 2 foot, 2.67. 32 inches, 2.8 inches. Okay, 2460. That's 5 miles. We check 5 miles. Sorry, I need to make this a little bigger so we can see it all. 5 miles should be 16 feet. 16.8. 16 foot 8 inches. We'll come over here, say 5 miles. Sorry, that's more than 5 miles. This one, 5 miles, 16 feet, 8 inches. That line right there, 16 foot, 8 inches. Go 10, 25, whatever, so my calculation, 10 feet, 66, or 10 miles, 66 feet, 25 miles, 1,000 feet. That's not 25 miles, is it? 25 is 132. 132 is that one. Sorry, I got ahead of myself. 416 feet, 25 miles, 416 feet. So this is matching up, okay? So the short distances, they're matching up. What about the longer distances? Let's look at this one. This is 100 miles now, right here, okay? 100 miles, 6,669 feet at 100 miles. Let's check my calculations, make sure that's right. 6,669.41. So 6,669 feet. That's at 100 miles. That matches my calculation. All I want to say is my calculations are right. That's how I'm figuring the curve of the Earth. That's how I'm figuring all my calculations that I'm doing all my tests on. So if anybody has any questions on that, that's how I'm figuring it. I think that's correct. If anybody has any problems with what I'm doing, please let me know. The only other thing I want to talk about is the why it doesn't matter whether it's 3959 or 3963. Because if I change this to 3963, change that to 3963, you can see my my feet has changed now to match that. But what is interesting is this doesn't really change. It's still 8, 32, 72, 128. It doesn't change. If I hit the undo button, watch 5 miles, 16.65, 16.67, 200 inches. It's still 200 inches. It's still small distances, doesn't change at all. Let's say 100 miles. What's the difference at 100 miles? 66.62 versus 66.69. That's 7 feet at 100 miles, and you're talking 66,600 feet, and you're talking 7 feet difference. That's why I'm saying it's insignificant. It doesn't matter if you use the pole-to-pole equation or equator equation. It doesn't matter. It is so insignificant that, well, I guess I'm using the mean. Okay, so maybe if you use that a little bit more, it might double it, or it might be 14 feet in 100 miles instead of 7. That's still insignificant. It still doesn't matter in the grand scheme of things. So if you can just use the average of 39.59, it's going to be close enough, even at 500 miles. What is it at 500 miles? Now you can see 500 miles. The furthest I've been able to see is 130. I know some people have said they've been able to see farther. I know I've seen 130 miles. Got pictures. I will post those eventually. So let's just go to 150. Well, let's go to 300 miles, because we'll get into Hawaii a little bit later, and I'll show you some interesting things there. But that's 300 miles. 300 miles is 60,000 feet of drop, by the way. 300 miles. 60,101. Okay? If we put that in at 39.63, the widest it is, we go down to 300 miles, it's 60,040. That's 60 feet. That's only 60 feet of difference. So now if you say, okay, well, I'm using the median and I'm looking at the widest, so if I look at the smallest, okay, let's double it. It's going to be 120 feet. In 60,000 feet, that's insignificant. Doesn't matter. Don't worry about it. That's proof why it doesn't matter. Just use the median, or mean, however you want to call it, of 39.59, and it's good enough. It's good enough for as far as you'll ever be able to see. And even that 300 miles, you're not going to be able to discern 60 feet. You just won't be able to see the detail good enough to be able to see that. But you will be able to see if you can see something that's 60,000 feet tall or not. I mean, looking at this, if I'm looking out 300 miles, from my vantage point, something has to be 60,000 feet tall. If I'm looking at sea level and looking at 300 miles, that object 300 miles away has to be 60,000 feet off the earth for me to see it. Okay? Because if I'm here and I'm looking out, let's just see, I think I have one that's 250 miles. What was 250 miles? That would be right here. So 13, so 1,320,000. So if we come into here, it was 250 miles. Oh. That one right here. Yeah. So we come down here, that's 41,000 feet. Okay, if we draw a line, let's just do this real quick. Let's draw a line. From this point here, okay, so that's sea level, from that point to where sea level is at the beginning. Okay, let's see, zoom all the way in so make sure we get the right point, right there. Okay. Oh, I'm drawing a horizontal line. Hold on, let's go back. We gotta take this north thing off. Try to do that again. So we draw a line. We'll take it from this point this time first. Okay, right there. That's my vantage point. That's where I'm looking from, and I want to see 300 miles away. Well, on a globe Earth, I'm looking at this point right here, right? Okay, that's that this is that purple line right here. That's a straight line. That should be my line of sight to be able to see that far. Can I see that? I mean, you can see how far I'd have to be looking in. In order to see that, I would have to be looking down. Remember, this is 1 mile, looking 1 mile away. I would have to look through. Wow, that's even closer than I thought. It'd be crossing right here. Remember my white line? Huh. It doesn't even cross. Like, I can't even look out and down. Do you guys understand what I'm talking about here? In order for me to see that point, I have to look through the water. If I'm studying the ocean, and my head's bobbing in the water or whatever, and it's completely glass, there's no waves, there's nothing there. I'm looking through the water in order to see that point. Does that make sense? That's how far of a drop it's going to be. So this object, if I wanted to really be able to see that, you know, if I wanted to be up there, this line, I would have to move up a ways to say there in order for me to see it. Then I can actually look out tangentially across the water, and it won't cross the line. It won't cross that line, because there's a lot of people that say, if you look it up anywhere, how far is my horizon? If I'm 6 feet tall, my horizon should be 3 miles. If I'm standing at the shore and I'm looking out, my horizon is at 3 miles, and beyond that, now the curve of the Earth starts to take over, and stuff should start to disappear behind that. So what I'm saying is, if I want to look at an object that far away, well, in order for me to really see it, it needs to be 41,000 feet tall. Because if I move this down anywhere, okay, let's just put it there arbitrarily, oh, that's halfway through, it's going to cross this line somewhere. And what that means is I can't see anything below. It's not even below that, below further than that. It's really below that line there. But I can't see anything below that because of the curve of the Earth. It has to be taller. Unless it's 47 or 41,000 feet tall, I won't be able to see that. So anyway, in a nutshell, that's the math of the curvature of the Earth, or the globe Earth, or the math and how the roundness of it is. Anybody has any comments or questions, or thinks I'm doing something wrong, I'd like to know, because that's how I am basing all my calculations, and I think that is correct. So anyway, I will have more video on some other things later on, so stay tuned. Anyway, that's the math of the globe Earth.